third video in Unit 2 on multivariate calculus. Today we're going to be diving into vector calculus and talking about gradients. So gradients are of a high importance in machine learning because this is how we optimize the networks and actually improve our results. So gradients are pivotal, essential to the process of machine learning, and they're going to combine the concepts of derivatives that we have talked about up until this point and expand them a little bit farther. So let's go ahead and dive in and cover this important topic. So returning to partials. In the previous lecture in video 1, when we were talking about partial derivatives, we noted that we could have the derivative with respect to x and the derivative with respect to y. Instead of kind of having these partials floating around, we can actually organize these into a vector. So we now have a vector with two different partial operators, the first being the partial with respect to x, the second being the partial with respect to y, and so on and so forth. And this is actually called the nabla operator. This is the gradient. So this upside down triangle is going to be equal to the partials with respect to the first variable, which is x in this case, times the partial with respect to y. Oftentimes, they're also going to see the partial with respect to z, since we live in a three-dimensional world, so dx, dy, dz. In this case, we're just going to start with dx, dy, and then we're actually going to expand it a little bit later. So this is the gradient. It can be thought of as an operator, and this operator is just going to be the partial derivatives for every single variable in the equation of interest. So let's look at that a little bit more here with some examples. So if we had the gradient for f of x, y, this would be the same as writing the partial of f with respect to x in the first position in our array, and then the partial of f with respect to y in the second position of our array. So if we actually have a formula or an equation here, 3x squared times y, this has been the equation we've been using up until this point. The gradient of f of x, y in this case would simply be the both partials. So the first being the derivative with respect to x, and that derivative being 6xy. We think back to our partials, we're going to hold the 3 and the y as a constant. So the derivative of x squared is just 2x. Multiply that by the 3 gives us our 6xy. In the second position, we are going to have the partial with respect to y. So holding the x squared constant in this case, as well as the 3, the y just drops out, it becomes 1. So we are left with just 3x squared. And now the output for this is as well a array of length 2, just like our gradient was an array of length 2 with both different partials here. So this is the gradient operator. It's simply the partials with respect to every variable in the equation. But what exactly are we finding here, and what does it mean? So let's talk about that. So like the derivative, the gradient is going to represent the slope of a function, or alternatively, if we think about our other concept, it's going to represent the rate of change. And so the gradient is actually going to point in the direction of the greatest rate of increase of the function, and its magnitude is going to be the slope in that direction. So this is invaluable because we can determine the direction to change our variables that is going to have the greatest impact. In the concept of machine learning, we are going to actually go in the negative gradient direction. And so if we had a loss function and we are able to calculate the gradients for our weights, we now know which direction to update the parameters to minimize our loss function. And that is ultimately what is going to drive machine learning. And that is actually convex optimization, which we will dive into further in the next video. So let's look at some gradients. Graphical representations are always a good idea. So here we have a color map of the function x times y squared. So the color in the background is representing that. In the far top right corner, we see we get 1,000. Because if we plugged in an x of 10 and a y of 10, we'd get 10 times 100, which is 1,000. So that is the yellow. In the far left, 0 times 0, we have 0. So if you thought about this in kind of a three-dimensional sense, you'd have a steep hill going up into the right, and the white arrows here are going to equal the gradient at all of those particular locations. So if you see in the bottom left, the slope is very minimal. The magnitude of the slope is going to be represented by the length of the arrow. The direction of maximum increase is the direction the arrow is pointing. So in the bottom left, we have basically no arrows. There's basically no slope. It's very small. It's only increasing slightly. But in the top right, we have a huge arrows because the magnitude of the increase or the slope over in this section of the graph is going to be significantly larger. And that is why they are increasing in that way. And they're pointing right up into that top corner. And so our y squared here is the biggest difference. So if we look along the y-axis, with x is equal to 0, we are going to get a partial that is pointing only in the x direction. And that is because the partial with respect to x is going to be y squared. So we still have a partial in the x direction, whereas the partial with respect to y is going to be 2xy. And then when we're plugging in a 0 for x there, so we're going to get a 0 for that entire partial. So there's no y component along this y-axis. There's only a strong x component pointing to the right, an exponential component. And similarly along the x-axis down here, we get very small values as well. It's a little bit different there because we're plugging in a 0 for y, which essentially cancels everything out as well. So this is a map of the gradients of this function, and we're actually going to reproduce this example in a Python programming project using matplotlib. So hopefully that will give us a better understanding of gradients, and it will also allow us to play around with a couple different equations. We can do something other than x times y squared, and we'll see how the gradient behaves in different situations. But in general, if we go back to our conceptual understanding here, the gradient is going to point in the direction of the greatest rate of increase of the function, and its magnitude is the slope in that direction. The direction is going to be key, and the magnitude as well comes into play, but mainly we want to know what direction to head into to increase or decrease the loss in the context of machine learning. Oh, sorry, I'm heading the wrong way. All right, so let's go on. So gradients are not restricted to 2 dimensions. We just looked at a 2-dimensional example. They can easily be expanded. And in fact, you're typically in the context of physics or math in general, you'd see the gradient with this partial with respect to z as well, because typically we're living in a 3-dimensional world, so we're going to have an x, y, and z component. So the gradient now of f of x, y, and z is going to be the partial with respect to x, the partial with respect to y, and the partial with respect to z. But this is, of course, course focused on machine learning, and in machine learning, we rarely stop at 3 dimensions, and we rarely have just one equation. So these gradient vectors can be organized, the partials for a scalar function, and if we have multiple functions, we're going to use the Jacobians. So this is going to be a vector of gradients now. So if we had 2 functions, we have f of xy and we had g of xy, the Jacobian is going to be the gradient of f of xy in the first position of our vertical vector here, or our column vector. The second is going to be the gradient of g of xy. And this is going to produce a 2 by 2 matrix. Since we have 2 partials here, we have the partials of f with respect to x and with respect to y in our top row, and in the second row we're going to have the partials of g with respect to x and the partials of g with respect to y. So this is the Jacobian. We're simply organizing multiple gradient vectors and their partials into a larger matrix. But again, why stop there? Let's tack on a few more variables. So instead of just x, y, z, we're now just going to call these x. And notice the bold, because this is actually a vector. It's going to be a column vector with x1, x2, x3, all the way to x of n, which is going to be any number of inputs or parameters that we so desire. So now we have a vector, it's just x. We're replacing the y and the z with x2 and an x3 respectively. So now the Jacobian expands as well. We're organizing all of these gradients, and instead of f and g's and other letters used to denote these different functions, we're just going to call them f of 1, f2, f3, all the way up to f of m, however many numbers of functions that we have. And notice the bold on the x again. This is going to be x1, x2, x3. So our partials now, the first is going to be the derivative of x1, or with respect to x1, and then the second, the derivative with respect to x2, all the way to the derivative with respect to x of n, however many partial derivatives we have to take. And then that goes down as well. So in the Jacobian, the output matrix here would go to f of m, so for however many functions we have, all the way to the derivative with respect to x of n of f of m. So this can expand quickly and rapidly, and we can calculate these gradients for larger arrays of equations. And this is going to be important in machine learning. We're often working in high-dimensional spaces. So we need to use these derivatives and these gradients in high-dimensional spaces, which is why it's a good idea to write these as this general case. Okay, so this is gradients in a nutshell, as well as a little bit about the Jacobian. We're actually going to reinforce and practice this knowledge in a Python programming project. So I hope you follow along in that as well, because it's actually going to help you gain an intuitive understanding of what gradients represent. So stay tuned for that. In our next lecture, we're actually going to move on to convex optimization. So how do you use these gradients to actually minimize a function? Or in the context of machine learning, this is going to be minimizing the loss function that we choose for our neural network or machine learning algorithm. So stay tuned for that. Thank you very much for listening.